Welcome to Mechanics webinar for the Subject Audit Enhancement course, Secondary Maths. And to start off, we're going to be looking at a little bit of theory. It's really just talking a bit about numeracy difficulties and barriers to learning maths. And then we're going to look at mechanics, and in particular, we're going to look at modelling and kinematics a little bit, and Newton's laws of motion. So just in terms of thinking about issues that you will probably have come across already, I'm sure. Dyslexia, I mean, there has now been very well researched and studied for many years, and everyone's very aware of some things that they can do to help kids with dyslexia. Not so much in maths, maybe. But obviously, if you're dyslexic and you have issues processing language-based information, whether you're in an English class or a business class or a maths class, there is still a lot of language-based information in maths. However, dyscalculia is really not very well researched yet. It's just starting to emerge as something independent in itself from dyslexia. And that's not to say that people with dyslexia don't have both, as it's a whole spectrum. All of these three are a spectrum, and you'll find that people have all three very extremely badly, and some may have just a little bit of dyscalculia or dyspraxia or something like that. So dyscalculia it's a lot of things, but it's sort of the difficulties with numbers and acquiring mathematical skills and concepts. And the dyspraxia is more to do with coordination. It prevents messages being properly transmitted to the body. And so all of those three can cause very poor working memory. The short-term memory just isn't really there, or they struggle to memorize and recall. Difficulty with processing and writing symbols. I mean, if you imagine that you struggle with English and then you've got to think about doing it in basically another language, that can obviously cause problems. And then the depth of mathematical concepts can also be problematic. Now, all of these are caused, I mean, I've sort of put damage to parts of the brain. I mean, it's just basically the way the brain is formed has sort of created those three conditions. Have you come across any of these in any of the lessons that you've been teaching?
Yeah, I've come across dyslexia, but I haven't come across anybody who's been diagnosed with dyscalculia yet. But I have also come across dyspraxia. So as you say, dyslexia is one that I don't know, 10 years ago you were guaranteed a statement for. Nowadays, not so much. So for that, the big one for us is extra time during assessments and the recording of that until I think it's year 9 when they box and get the guarantee of I'm in the GCSE. So we've got to evidence that. Yeah. Going up to year 9 to make sure that it's essential.
Yeah, absolutely. And I mean, it's just it kind of was one of those things where sort of everyone got on the bandwagon and was like, oh, I must be dyslexic, and I think that's what caused sort of the wariness. But then on the other side, because it is a spectrum, maybe there are a lot of people somewhere along the scale, and dyscalculia, I think. Had you mentioned that 10 years ago, people would have laughed in your face and said, you're just making this up, really. You're just saying you struggle with maths, basically. But they're now starting to think, well, if you've got an issue with processing language-based, then, why not with maths?
Yeah, exactly. I'm sure it'll catch up with dyslexia.
They don't really have a test for it, particularly, that I know of. Schools.
They didn't for dyslexia either now, do they? But apparently a nice donation to the Dyslexia Society, and this is this is the word that spreads around amongst the SENCO and people like that.
Have you had much on throughout the program? Have you had much about SEN?
No, I'll say no. We've had a bit, but it is always quite general. So
Yeah.
And I guess most of it is what you are going to happen across within the workplace. So most of it is just raising an awareness and then liaise with specialists in order to try and work out what the best method for dealing with that is within your classroom.
Yeah, and I think it's like everything, isn't it? It is all about tailoring it dependent on the student, because you have high functioning dyslexics hide it very well, and you think that they're absolutely fine, and then they go into an exam and you're like, what happened? And yes, and it's just because they struggled because they didn't have that extra time, and often, unfortunately, that's the first place they then realise. So sometimes you get the GCSE kids so that you thought were going to do amazingly well coming out, and then they're only diagnosed when they go to college because they've managed to they've found a way to work around it. And that obviously is what we're aiming for, really, is that they've got to find ways to make up for it rather than using it as an excuse, of course. So yeah, hopefully we'll discover more, maybe hopefully, about dyscalculia. And but again, I remember asking one of the students in my class about the different colours, and that's been, people have said, oh, actually that's a myth that they like to look through different colours, but actually and I'm sorry that this screen is quite white today because I should make it slightly different colour, but reading stark, what do they call it? I can't remember. They don't like that. It hurts their eyes. Kind of visual. What is it? Visual stress. Visual stress is common with dyslexia, and so, but only something like a quarter of them. So it totally depends. Some of the kids will say, yes, I'd really like it all printed on green paper. So you do that for them, and other people go, I don't care at all. And it's the same. You'll come across, what it is, and unfortunately, what seems to happen is that because very common thing is the poor working memory and this ability to sort of, the goldfish syndrome where they've forgotten it all the next week. But what tends to happen is you fall back into this whole, okay, look, we'll just try and teach them by rote, just trying to get something to stick. But unfortunately, that then means, because they struggle with that, and if they don't have the understanding, that they've basically lost it completely because they've got no way of storing it. So I've put, bold, visual, lots of visual things, of course, providing opportunities for discussion, because, so many dyslexics, when you talk about things, they're so eloquent, really interesting, really have an opinion about it, and then they're just struggling to get it down on paper. So if you can examine maths by discussing it, then it will stick for them in their head, so that they're not having to do loads of exercises. Well, I mean, they still have to try, obviously. And then, the mathematical instruments and time for writing, especially if you're dyspraxic, that's something that the dyspraxic kids are really going to struggle with. And I remember, I wonder how many of the kids at school that were called clumsy would now, be called dyspraxic, and not just sort of told off all the time. But yes, it's all just about different representations of things. So, they'll struggle with the algebra, really struggle with the algebra, because it's letters and trying to write things. So, connecting that to the graphical stuff and geometry. But the other thing I was going to talk about as well is maths anxiety, or, I mean, because it's kind of an American thing, math anxiety, is a real thing. I'm sure you'll have come across loads of people who, when you tell them that you're going to teach maths, are just like, oh, that's awful. That's my worst thing ever. I mean, they really have this sort of disgust about it. But that goes further. There are some people who have such a fear. It basically is a mental block for them, and they're facing such anxiety that when they get into a maths lesson, they're not listening. They can't cope. It's, well, the amygdala is saying, right, this is the fight or flight. Let's flee. And so you've got to just get them switched on to do the no, let's fight. And yeah, there's a test for it called the MARS, the Maths Anxiety Rating Scale. And if you, I suppose if you have got some kids who really seem to be very anxious about it, you could sort of say to them that this is a condition, and just talk to me about it. We can manage it. But I've put some reading here about it. Chin is particularly good because he covers all of these different things. So he covers the dyslexia and dyscalculia and stuff, and the math anxiety. Basically, just talks about all sorts of things that basically affect you learning math. And he's put, well, quite a few golden rules, really. Obviously, don't create anxiety. And I think we do create anxiety all the way in primary school with maths, because this is, again, it's all about speed and rushing and having to do things fast. And for these guys, that's just the worst, because they just can't process it fast enough, and it shouldn't be a race. And then just, making sure that they achieve and don't feel that they're failing. And as I said, individuals teach more than one ways to do things, as we were saying, just do it different ways. And yes, as it says, understanding is a more robust outcome than just recall. And this is where, when you come across the teachers who do just do this is how you do it 100 times, and then you've got it. That process, hopefully, yes, by doing it lots of times, there might be some automation happening, as there will be for everyone. However, in an exam, the anxiety causes them to forget everything. And then if they don't understand, if they never understood, then they're just stuck, basically. So, yeah, they need to go for sort of understanding side. Yes, and then it says, mentions method, all the above rules have exceptions, so who knows? Anyway, that was all I was going to say about that. Have you come across any kids that genuinely seem anxious about that?
No, I haven't. Not to the extreme that you would diagnose something. I think as you say, the societal view is that it's okay to be rubbish at maths and all maths. There's that stigma attached to it. It's still got that cloud over a lot of people.
Yeah.
And not but not to the point where it's you could diagnose it in somebody, particularly not in any of the classrooms that I've worked in so far. But a lot of this is really it's standard things, isn't it? But it's all that stuff to be avoided. So it covered a lot by creating that safe and stimulating environment. Failure is good. We want people to fail in order to succeed, and they're not alone, etc. And teaching everybody.
This should be happening at primary level, hopefully. So anyway, let's start with some maths. So today we are looking at mechanics. When I talk about mechanics, the
not changing oil.
No, exactly. Not changing oil. It is actually the study of motion in mathematics, and it covers a lot of material because it forms a whole applied module. Like statistics and decision mechanics is another option that they can choose at AS level. And there's an M1, and then the following year they could do M2. So today we are just going to look at maybe not even a third of M1, but just a little bit of it.
All right. So what they do in a year, we're going to look at in these three hour sessions.
Oh no, they do it in a third of the year, because they'll do Core 1, Core 2, and M1.
Oh, right, yeah.
Yeah. So a third of the
year. That's a lot more realistic then.
So a third of a year and a third of that. So let's say a ninth of a year in the next 3 hours. No,
so they're doing M1, M2, S1, S2. Is that the kind of thing? Yeah.
It depends.
Or C1.
Actually, they have to do C1 and C2, and then they can do S1 or M1 or D1.
C1 and C2 are compulsory.
Yeah, those are the core modules of pure maths.
Part of the A level, and then the other, they can pick 2 of the others, can they?
They can pick one of the others. So they just do 3 modules. And then the following year, they have to do C3 and C4, so 2 more core modules. And then they can choose another applied module. So they can either choose to continue with the one they started. So if they've done S1, they can do S2, M1, M2, D1, D2. Or they can do a different one of the applied modules. And actually, for example, if they do S1 in the first year and then decide to do D1 in the second year, they're basically doing AS level modules each year. So it's a little bit easier because the 1 in front of it shows that it's an AS level rather than an A2 level. So that is a slightly easier option than perhaps doing S1 and then S2, marginally. So that's what they sort of do for some of the students who aren't bothered about their applied things. If they want to do physics or any sort of engineering, we say to them, you have to do M1 and M2 because this is all the basis for anything like that. And Newton, honestly, he must have been the busiest person ever. He came up with modern mechanics because...
I don't know, did he have kids?
He did, I think. I think he had a wife.
Did he? All right.
Although
I'll put him into that.
he wasn't supposed to not be a very nice person. But, you know, who knows? It's like Stephen Hawking, isn't it? Actually, he's done a lot. And both of them are narcissists, basically. You know, I suppose you have to be. And it's very typical, you know, being a mathematician or a physicist, you are very much focused on that, and probably somewhere up the autistic spectrum. So anyway, he published 2 huge books about this. But the idea is that with all applied maths modules, there's this modelling, what do we call it? Modelling, well, basically there's a flow chart that we follow, where we set up a model, analyse the problem using the maths. So this is the sort of the bit without anything else. You'd just be doing the maths. Then you interpret what you've done with the maths, check whether it makes sense. Then you modify it and go back around again to set up the model again. That's it, the modelling cycle. That's what it's called. That's what's meant to say that. So all applied maths is that. I mean, you could do it whether it's a statistical model, decision model, or mechanical model. And part of going into the applied module is that the students are expected to vaguely understand that that's where the maths fits within the real world, is that we use it within this modelling cycle. So, for example, if you were to think about rolling a full tin of Coke down a slope and an empty tin down a slope, what's your first instinct as to what will happen?
The full tin's going to get there first.
Right. So that's your model, and then, you know, if you knew the maths for that, you could then calculate it, making some assumptions about it. So you think to yourself, okay, well, what assumptions do I need to think about? And then you're faced with the shape of the tins being the same and everything being the same. And does the slope have friction? Is it smooth? And that sort of thing. And then it would be good if you could test it. Do you know why? The full tin of Coke gets there faster?
I will say resistance. I don't know. No.
No. Well, hopefully by the end of today. I can
hear you laughing now.
But hopefully by the end of today, you will know a bit more about that. Oh, here's the modelling cycle. Sort of specify the problem, make assumptions. So we're going to talk a bit about assumptions now before we get into how we would use, before we get into the maths that we use. So in the mechanics M1, they use a lot of words to describe things, and those are quite important. So if you see something and it says a light, inextensible string, that means they have already assumed that the string itself has no mass and it isn't stretchy because, well, I don't know about you, but I'm not very good at things. Well, no, I do know the math actually. However, that's quite advanced maths, knowing how something stretches. So if you imagine a weight on I should have got some pulleys and stuff to do this to show you on the webcam. But if you imagine a weight on a piece of string, or just a ball on the end of a string, and it's just a piece of string itself, so it's not stretchy, then you can just think about the ball that you've got on the end. You don't have to worry about what is actually happening with the string. However, if it was made of elastic and it's springing up and down, that would just make the math a lot more complicated. So in M1, they don't have to worry about strings being elastic. They don't have to worry about how much the string itself weighs, only whatever's attached to it. We talk about particles instead of thinking about the object itself. So if we were talking about a car, and I know this might seem ridiculous, but the reason that we model it as a particle is that we don't want to have to think about what is happening to it from all different angles. We just want to think about it happening in one plane, because again, it then becomes too complicated for us at this level. Obviously, you know, for people doing very complex calculations, to do with how cars go and that sort of thing, they would have to take into account all these different things, but they're very gradual. Rigid means, as you would expect, that you can't bend. Small, again, is like particle. And smooth, if you see something describing something as smooth, it means we can ignore friction. Now, let's talk about when we think it is reasonable to disregard resistance. So, do you think it would be reasonable if we think about air resistance at the moment in the following situations? If you drop a marble from an upstairs window, do you think that's going to have enough impact on that we should consider it in the disregard?
I would say no.
A marble dropped from an upstairs window, because of the smoothness of the marble and the fact that we're not really, really, really high up, the air resistance probably isn't going to, it's going to be so marginal that we disregard it.
Yeah.
But it's very hit and miss. So a table tennis ball, only a little bigger, really. I would have said a tennis ball, maybe I should have said a tennis ball. You see, I think on the other hand, that... Yeah, exactly. You sort of be like, well, it doesn't get a bit bigger, it's going to have more impact on it, what's happening around the sides of it. A marble dropped from an aircraft, which is only at 2,000 meters altitude, so much higher than the window. What do you think?
So no.
Yeah, you're getting an agony. Exactly, because as it gathers speed, there's going to be, a lot of resistance as that comes down. A shot put. So a shot being put. You think about holding a shot put.
I would say no.
Yeah.
Because it has to go up and I thought it had to go up and down. So
yeah, I was thinking about this too, and I was thinking, well, does it just go horizontally? There is a bit of down, but it's not very far down, is it? Because it's only coming from your shoulder. And often with horizontal things, we ignore it, but I think it's only because it's not very high. A firework being set off?
no.
probably disregard it. I think you wouldn't want to. Obviously, you couldn't disregard the wind, but air resistance, because the rocket's going to kind of cut through it.
Yeah.
Probably. No, this is very tricky. And do you know what? Luckily, you don't
Why
have to
why
know
are they why are they made aerodynamically then? If resistance isn't an issue. Thought for the day.
Yes, I put these with you having to worry about it in mind. So in
Yeah.
M1, someone else has designed that rocket. You don't have to worry about it.
Okay.
But no, but you're right. It does say probably. So it's saying, yeah, you do probably kind of. Well, it's not really clear, is it? Child on a swing in terms of which way did I phrase it? To disregard. Yes.
Disregard, yeah.
So again, because it's only a small motion, um, it's probably not going to have very much impact. Person walking again, you can probably disregard it.
Yes.
But the person cycling,
Well, I'd say that's clearly no.
nothing to do
It
with it.
depends.
Yeah,
It depends what the cycling. Tour de France, hey, yeah, that's what drafting's all about, isn't it? But a guy
yeah,
going to the
exactly.
shops,
Yeah, yeah. If you're only going at the speed of the person walking,
yeah.
it probably doesn't matter. Now friction, would it be reasonable to disregard friction if you're skiing downhill?
No, because you try and reduce friction because you wax your skis,
Well,
you
exactly.
wax your snowboard.
Because you've really, really waxed your skis,
Okay,
the
then you should
friction,
be,
I think, would have
yeah,
been reasonable to disregard. I think for us modelling it, so if we're imagining a skier going down a hill,
yeah,
um, and thinking about what's happening to his motion, the friction is incidental, isn't it? Because let's imagine, yeah, he's really waxed his skis, so that there
yeah,
isn't friction, basically,
yeah,
so that he's made it smooth. Child going down a
yeah.
slide. That's a difficult one,
Oh,
I think.
see, um, then if they were going down, here we go. If they're going down on their skin, that's
Yeah,
going to lead to friction.
yeah,
Yeah.
yeah.
So
So
this is with hours spent at soft play areas.
yes,
Okay.
exactly. Yeah.
I don't disregard it because I put trousers on them to make sure that they avoid
Absolutely.
the
Yeah.
friction. Then I can disregard it.
Yes, exactly. And then, anytime when we have, when they do children's birthday parties in them, and my daughter wants to wear a dress, and I'm like, I'm sorry, I know it's a party, but you cannot wear a dress in soft play. So,
Yeah,
no,
well said.
exactly. So you can disregard it if they're wearing trousers, but if they were just going down it bare-legged, you'd have to say no. Um, yeah, so raising an object on a rope. So if you imagine you've swung a rope over a tree branch and you're trying to lift it over it, do you think you could disregard the friction?
Again, I'd say no.
Yeah, yeah, it's going to be quite important, isn't it? Because that
Hmm.
actually is going to be all um, the difficulty probably. However, if it was over a pulley rather than
Yeah,
over a tree
on a
branch,
tree,
yeah,
that friction transfers to heat. On a pulley, then that's not so much an
yeah.
issue.
So a car being driven along is
Uh, I'd say you could disregard it. Yes.
it's difficult because while it's being driven, that's fine. I suppose if you brake, oh, in fact, friction needed for wheels to provide the forward force. So yes, sorry, you can only drive a car because it grips to the road. Without friction, if you imagine driving on an ice rink, the car would just glide, wouldn't it? It wouldn't be able to drive in the straight line because
Okay. Yeah.
without friction, it would just glide. And equally, round a curve, um, no, you definitely need to think about it. Anyway, oh, what I was going to say is in M1 they disregard air resistance, so you don't have to worry about it at all. It is completely disregarded. Anything that's dropped, we're only considering other things that are happening, unless they say. So they might say the resistance is this much, and that resistance could be made up of a number of things, including air resistance. Friction, on the other hand, over pulleys and some smooth surfaces, they will say smooth, and so you don't have to worry about friction. But generally, most surfaces have friction, so you have to account for it. So I'm just putting in a little bit in here now before we get to the sort of, I don't know, the proper mechanics. Kinematics is obviously part of mechanics because that is the study of motion, which is what mechanics is. And as we said before on the very first webinar that I did with you guys, we looked at quadratics and a tiny bit of kinematics because it's now in the GCSE syllabus. So this is a little bit that's been taken off M1, put into the GCSE as well. But it's still in M1, so they'll then be repeating what they've done at GCSE. And the very basic level of it is that, you know, speed is distance over time. That's at a very basic level. Here I've got a little thing for you to do. So I don't know if you know what Scout's pace is. It's when you walk and then run the same number of paces. So you might, you know, walk 100 paces, then run 100 paces, then walk 100 paces. So you don't stop at all. You just change between walking and running, doing the same number of paces. And that way you don't get tired because you sort of walk for long enough and then you think, actually, I quite want to run. Then you run and you think, oh, I need a bit of a walk. And in that way, this is how Scouts used to, in the war, get back from, you know, to get between wherever they were going quickly without tiring themselves out too much. So you've got a problem, which is how long would it take a Scout to travel 2 kilometres? So this is the sort of thing that you can give to the kids, kind of inquiry learning. There's nothing else to it, right? So that all they're saying is, okay, how long would it take a Scout to travel 2 kilometres? So if we think back to the modelling cycle and think about first, well, you have a go at doing it now. Just have a think. And obviously this would be very nice in groups because people will be saying, well, they'll be saying, well, let's say you haven't told us what, you know, how many paces you're going to do and how do we know how long a pace is and all of this. So that's hopefully what's going to generate discussion. So if you have a go, just note down what your assumptions are and what you think, figure it out. Why they did the same.
I have used all my knowledge to establish that it is 20 minutes
20 minutes.
to do 2 kilometres.
Okay, yeah, I can see that. So what did you assume?
Well, I assumed that the walking pace was, what did I think, 4 kilometres an hour if you walk.
Yeah.
And then I did, I multiplied the, sorry, I divided the where did I go? I multiplied the 4 by 2 because I thought that would be a reasonable assumption for walking and jogging. So
Okay.
running, I thought you could cover 8 kilometers in the hour, but then I sort of backtracked on that. I thought that was a bit ambitious, so I thought 6 in an hour would be more realistic, and hence divided the 6 by 2 to give me 20 minutes.
Right. Interesting, isn't it? Because I was just thinking about this, and I also I walk at 4 kilometers an hour, so I agree. And then I think, well, I think my sister does a 10K in 30 minutes. No, maybe that's not right. That must be a 5K. So anyway,
10K, yeah, 6 miles. So that's really quick if she's doing it in.
she is very quick, but
Yeah, 6.6 miles, 10K.
right. So it must be that. It must be the whole.
So that's 5-minute miles.
Yes, I don't think she's Roger Bannister. So I think that must be a 5K. That she aims to get under half hour. I don't run at all. I don't really like walking either, so you know. So let's see, what did I put? So yeah, so in terms of the kids though, you know, there'll be some of them that have some sort of idea, and obviously loads of them who have never been outside their rooms practically. So there's also the case of if you're running and walking, do you make the assumption that the steps are the same length? Although that might not be strictly true, because you might have a longer stride as you walk. It's easier to think of it as just being the same. 1 meter is probably fairly large stride, I would think. I would think maybe half a meter. That you're running and walking at a steady speed, absolutely. So that's an assumption that you've got to make rather than like speeding up too much. You've got to assume that once you are running, it is all the same speed, and then once you're walking, that's all the same speed. Yeah, the suitable speed. So that's what we thought about. How many paces? So you hadn't sort of broken it down into terms of this running and walking. So how many do you do before you change? Because that might affect it. So, for example, this one assumed that they walk 40 meters in 40 seconds. Oh, but it takes them, so they're sort of a third of the time when they're running. So I sort of gone, so for 80 meters, it's taken them what looks like very, very quick, basically a minute actually to do 80 meters. Let's do 80 meters. Well, if you think about the 100 meters, oh gosh, I can't think back to that either. But the 100 meters race.
Yeah, that's about 10 seconds to run for an elite athlete.
Yeah, I was going to say, it used to be like 12. I could never get below like 16 seconds. So yeah, that actually, because of the walking in there, that's quite long really, isn't it?
Mm-hmm.
So that's sort of saying, oh, I haven't done the calculations. So based on that, I'd say, okay, so 2,000 divided by 80 times 53 the third. What have I come up with there? Seconds, so that's seconds. 22 minutes. So there you go. So
yeah,
there's this feeling, isn't there? We have a general feeling that would take you about 20 minutes to do 2 kilometers. The kids themselves may not have any sense because they may that sort of sense of distance and kilometers versus miles, and any of that may just be anathema to them. So it's, you get them coming up with ridiculous scenarios. But that is the whole reason for all of this. It's all very well being able to do maths, but ultimately, not many people spend their lives just doing pure maths with no reason for it. Anyone who does actually use maths when they leave school is using it in the sense of in an applied manner. So getting them to do these sort of problems gets them thinking about all the additional stuff that's important. And hopefully, for the ones that are like, oh, when are we ever going to use this? What's the point? This is going to engage them. So anyway, that was just a little idea for that. And then you've got to think back about how valid were the assumptions, and you can start to adapt things and change them. And, they could be measuring, you could give them some measuring things. They can measure their pace lengths and run across the classroom or outside. And then you can send them all out to run 2K, do the 2K run and walking, and have a free lesson. No. But ideally, you get them to do that, but isn't really very useful for us. Anyway, in terms of the kinematics formulae, as I said in the original webinar, they're expected to use these. These are for when there is constant acceleration. So here, in fact, so when we were talking about before, assuming that there was a constant speed, obviously then the acceleration would be 0, and so that would also be constant. But then you wouldn't need to use these because you could just use the basic speed as distance over time. So when there's acceleration involved and it's constant, then we can use what we call the Subat equations. And there's these 3 that they are given at GCSE. And then there's another one which you can get by taking these and just rearranging them. I think you sub one of them into the other, you get this one. At M1, the students have to learn these off by heart. So they have to sort of find a way to remember them. And one good thing to do when you're teaching them is getting them to write them out every time, so that they write them out every time they answer a question, and then they have to pick the one that they need, and that just gets them into the habit of knowing these.
That's a great idea.
I mean, it's pretty tedious, obviously, but the great thing is that once they've written them out every time, then they just automatically do it in the exam. And it helps because if we look at an example, so a particle, we're modelling whatever it is as a particle, so they don't have to worry about the fact that it may not be travelling directly in a straight line or have things happening to it. So a particle travels in a straight line with constant acceleration. Its initial velocity is 10 meters per second, and after 40 seconds, its velocity is 15 meters per second. So between that time, it's accelerated constantly, with constant acceleration. So it says, what is the magnitude of that acceleration? And the displacement after 40 seconds. Do you know what I mean by displacement?
No.
So we talk about distance, and when we are thinking about, when we're talking about just speed and time, like we were before, we were talking about covering a distance of 2 kilometers. We aren't bothered which direction. We're just assuming that's all in one direction, that they've gone that 2 kilometers. Displacement is distance in a direction. So in fact, you could have run for 1 kilometer and then come back for the other kilometer, and your displacement would actually have been 0, because displacement is all about your distance from your original location, the original position. So we talk about displacement because these involve vectors. Velocity is a vector, acceleration is a vector. That velocity is speed in a particular direction. Acceleration is in a particular direction, and displacement is also in a particular direction. So we often draw a diagram if something is changing. This is fine because it's just going in a straight line. I could have used the words speed and distance because it's all in the same direction. But going forwards, this is in mechanics in M1, we use, suppose, more complicated terminology, because then it applies to everything. So here we've written down, well, we've got 3 of them here. We're missing B equals U plus AT. And I think the reason for that is because we want to use that one. So I get them always to write SUVAT. So that's why I call them the SUVAT equations, because S is displacement, just to be confusing. I don't know why we don't use a D, but we use S. I really can't think. I should look that up, but you can send the kids away and get them to find out why on earth we do. The U is our initial velocity, and V is final velocity. A is the acceleration, and T is the time. So when we're looking at kinematics, we're looking at speed, acceleration, time, and displacement. So we write out SUVAT, and we have to think about what we've got. We've got initial velocity, so we know U. We've got final velocity, so we know V. And we've got time, so we know T. For the first one, though, we want to know A, so we put a question mark by that. So we then look at the ones that we've got, all the formulae we've got, and we say which formula involves U, V, A, and T. And it's this one, the V equals U plus AT. So it's really useful to get them to write out SUVAT, tick the ones they've got. They always then get muddled because they'll have 2, and then they've then got to look at what the question says, which is the one they want. They can either put a circle around it or question mark. They then compare those to the formulae and say, okay, I need V equals U plus AT, and then they can just fill in, substitute into that formula what they've got, and rearrange it to find here that the acceleration is 0.125. So, does that make sense?
Yes, I was just busy trying to rearrange the formula to get A to be the subject of the equation.
Do you prefer to do that before you then put the numbers in?
Well, it was just a kind of mental thing for me.
Yeah.
I was just trying to,
I don't know what.
No, I'd be happy to work with substituting the values in, and then leaving the variable, and then rearranging from there, or
Obviously, it doesn't matter
pretty much
either
what
way.
you've done.
Yeah, it doesn't matter either way, except I would say that, so they should write the formula down that they're going to use. If they then sub the numbers straight into that one, they'll get a mark for that. If they try and rearrange it, do it incorrectly, and then put the numbers in, they won't get any marks, unfortunately. So there's always an extra mark here to be gained. So I think that's just a plus point for subbing the numbers in, and also because, well, they find rearranging formulae very difficult, don't they?
Yeah.
And yet, although we know that it's exactly the same as when we're doing it with numbers, they don't seem to find that quite as bad. I suppose because they can then see, oh, I'm adding the 10, so I need to take the 10, and times it by 40, oh, I need to divide by 40. So you have a go at doing B, the displacement. So what's, oh, never mind, I can do it now. So you actually now have found A, so you've actually got everything. That's why it's saying you can use the 4 remaining equations. I generally say to my students, if I were you, because you might have made a mistake with the A, I would, unless you desperately need to use it, I would use the ones that you were given. Always use the ones you're given. So in which case I would say, actually, you've got U, V, and T, and you now want S. So which is the one that involves S, U, V, and T?
Well, I was going to say they all do, but just the second one down, S equals a half U plus V brackets T.
So I would be inclined to use that one because it doesn't involve using what you have calculated, which you might have done wrongly. It just guards against that. So they haven't. They've just selected that one because they can, and obviously they know they've done it correctly.
Just one for me. It's gonna, it's the old silly questions, the one you don't ask, but I'm asking it.
Yeah.
We've got for the solution to A, it's A equals 0.125 meters per second to the power -2.
Okay. Yes.
What are these?
Okay.
Why are these playing a part?
Let me just. I could have put instead. To write that
Sorry
the same
for
way.
having to ask this, but this
No,
is
no, you're absolutely right. I totally forgot. The students. Oh, whoops. Sorry, I'm just trying to find where my mouse is.
I'm not looking at any answers.
Oh, I'm just sorry. I'm just trying to.
I've closed my mouth, my eyes.
No, I'm just trying to. I've just got a pen that writes, but I can't figure out where I've got it. Where's the pen gone? So, okay, here it is. No, whoops. Sorry. Trying to master my new thing. I've got like a tablet to write on. Okay. This is rubbish. Let me use the mouse. Meters per second. Oh no, my mouse will work. It's rubbish there as well. Meter. Let me just try and figure out how to use this. How do I get the mouse here? Okay, here's the mouse. There we go. Meters per second. We write like that. Okay. If we think about velocity, so that is actually 10 meters per second. That's because speed, is distance over time. So if we think of the units of distance, that would be oh, sorry. Oh well. Okay, I have the idea here. Distance is measured in meters. Time is in seconds. And that's why our units for speed are meters per second, because the per just means divided by seconds. That's the units. Is that all right?
Yeah.
Does that make sense? Yeah. Now, if we think about indices, when you divide by something, it's the same as doing it to the -1.
Yeah.
So that's where that comes from. So meters per second is the same as writing meters
over S.
second to the -1. Yeah. So that is exactly the same. Acceleration. Acceleration is the change in speed over time. Change in speed over time. Yeah.
Yeah.
So speed is meters per second over seconds. So if I think about that as a fraction, meters per second divided by seconds is the same as meters per second times 1 over second, which would be meters over second squared. So we can say acceleration is meters per second squared, as I wrote down here.
Yeah.
And again, because of indices, we can just write that as meters second to the -2. Because 1 over second squared, for example, is the same as saying s to the -2.
Brilliant.
So that's why. Everything in math seems to come back to indices. Absolutely everything.
Yeah. Well, my indices have really improved, so I understood that, but I was just the fact that what is acceleration is suddenly meters second to the
Yeah,
mile.
and you're absolutely right. I should have done this because this is something that the students don't get either. They don't know this, and I would start by doing the same thing, exactly showing them all of this.
Yeah. Well, I know when Neil watches this back, he's going to be asking the same question, so I really asked it for him because he'll be
Yeah,
quite lost here.
yeah, that's great. Thank you. Let me raise this now and get up on that. There we go. Yes, so for the rest of this, you can just put it in. And yes, units are very important in mechanics because we have them. I mean, that's the difference. In GCSE, they don't really care at all, do they, really? I mean, units, centimetres, they're not bothered. But here, we now have to think, okay, is this metres or was it in centimetres? They're interested because otherwise it's wrong. So you've just got to get them thinking about all of this. So it's an excellent question because it's brought us around to about units. So now we're going to think, that was just a little bit about kinematics and horizontal motion. If we think about vertical motion and dropping a stone, it falls down towards the earth. Again, we model that stone as a particle and we're going to ignore air resistance.
Yeah.
Although we're saying it falls towards the earth, we're not saying it falls from a great height necessarily. So the only force acting on that stone is just its weight falling down. So weight is the force due to gravity. We are effectively weightless when we're in space because there's no gravity, it's in a vacuum. We don't have the force of our weight pulling us down. So we know that the gravitational force produces an acceleration. And that acceleration is approximately 9.8 meters per second. Occasionally, questions will say you may use 10. But I should imagine that happens less and less. I think that was at a time when, calculators weren't necessarily used, and it was a way that you could, approximate things. So the gravitational force on the Earth is greater than the Moon, for example. I can't remember what it is on the Moon, but it's something less than 2, I think. So we use the letter G to represent this acceleration due to gravity. So for anything that's falling and we're only worrying about its weight, we have to take into account the acceleration due to gravity. And so that acceleration will be equal to G. And so G is the letter that represents 9.8. So, like when you see pi written, and you know that represents 3.141, etc. G represents, G is the letter representing a number, which is 9.8. So what that means to us with kinematics is that if we're thinking about vertical motion now, before when we were thinking about the particle just going along horizontally in a straight line, we didn't have to worry about gravity. However, if you're dropping things vertically, we do have to think about what's happening with gravity. So here we've got a ball that's dropped from rest. Now we say that's important. So when you're getting the kids to figure out what is important in the questions, that's important. What does that mean from rest?
I'm saying it's from stationary.
Yeah. So that tells me something. That tells me that my initial speed will be what?
0.
Exactly. So effectively, when it says that, that's told them already that they know So ball's dropped from rest at the top of the tower, hits the ground 2 seconds later. So we're told our T. Modelling the ball as a particle and ignoring air resistance, find the height of the tower. So I now know I've got U and T, and I want S, confusingly, because that S is our displacement. I suppose that's why they don't use D, because it represents height, so all sorts of things. But the other thing I do know is because it's dropped vertically, I've also got A. So, let's see if I do this one. Oh, look, there's a nice little picture of the ball. And throughout mechanics, we really stress that drawing pictures is really helpful. So here's our ball going down, and we'd like to write little things by it. So at the top, oh, okay.
I'm sketching now.
There you go. So what we tend to do is we write the initial speed at the top, and I often use a single arrow for that to go with that, but they happen there. And then we know that T is 2, so when it hits the bottom, we know that T is 2. And then we use a double arrow for acceleration. Annoyingly, I've got a slide later about this because I thought that it comes up here. So, because we're just dropping it downwards, gravity happens towards the Earth's surface, so that is downwards. So everything here is happening in a positive fashion, if that makes sense, because it's all in the same direction. So we know we've got U, we've got A, we've got T, and we want S. So again, we write out our equations, which were back there, and we know that the ones that have those 4 is this one, S equals UT plus a half AT squared, which seems to be one of the ones that the kids remember the most. There are in fact 5 SUVAT equations, because there's another one which is S equals VT minus a half AT squared, and I don't tend to show the kids that because they then start to get very confused. So it's fine for them just to know these 4. They can get everything from those. The other one is just from rearranging the others. So we substitute in what we know is very nice, because U is 0, that bit disappears. So then we've just got a half AT squared. So a half times 9.8 times 2 squared is 4 times 4.9, which is 19.6. And I haven't been given any units, but I would assume being a tower that was meters. Yeah, so times 19.6 meters high. But in that case, because they hadn't given any units, it would be fine to just leave it. But we generally model things in terms of meters and seconds. So the speed would be in meters per second. You would then ask to find the speed. So when the motion's all downwards like this, we say downwards is positive, and that's fine. However, if there is anything going upwards, we consider the down to be negative. For example, a ball is thrown upwards. Sorry, I've put that over the thing. Let me just escape so I can see what that actually says. Oh, no, there's not escape. Cancel that. Cancel that. I don't want to press escape. Sorry to those watching this recording. I don't want. Okay. Can't see what this says, so I'm just going to change it here. 12 meters per second. Right, let's go back to this. So a ball is thrown upwards with a velocity of 12 meters per second and travels in a straight line, landing on the ground. So we're assuming that it goes upwards and straight down. So we model the ball as a particle, ignore air resistance. We want to find out how fast it's moving as it hits the ground. So let's draw a picture. Up it goes. Now, it's not really going around like this looks, but because the fact that you would then otherwise be drawing on it again, we show it like this. So we throw it upwards with a velocity of 12 meters per second, travels in a straight line, and then drops back down again. So we know that the ground is 1 meter below its starting height. So because we are measuring upwards as positive, gravity acts downwards. So in this case, our acceleration is going to be minus 9.8. So let's do again, that needs to be extended to be one line. And because we have landed, we're taking our initial position effectively to be the 0, we've landed a meter below the starting height. Again, that's in the negative direction. So that will be -1. So that's why we call it displacement, because the direction matters. And so the negative or positive sign is what tells us the direction. So again, we can go through our Subat equations. We've got our distance, our displacement rather. We've got our initial velocity. We want to know how fast it was moving as it hit the ground. So we want the final velocity, and we've got the acceleration. So I think we want b squared equals u squared plus 2as, looking at those. Yeah. So that's the one that involves that. So obviously, you know, when the students have also been doing it for 20 years or however long I've been doing it, then they will also just be able to pick out whichever one, but ideally you want to get them writing them all out each time. So v squared is what we need. U squared is 12 squared. And 2 times a times s, you've got to put it all in brackets. The 2 times minus 9.8 times -1. So they don't lose any of those signs. And that, in fact, makes it all positive. That's v squared. They've got to remember to then square root that. And that gives them a velocity of 12.8 meters per second. And then get them to think back and think, does that make sense? So it started off at 12. We've thrown it up in the air. And as it's come down, obviously we have got an acceleration due to gravity of 9.8, which has made it quicken. So that does make sense. It's a little faster, hits the ground a little faster than you threw it up. If they were looking at 128 meters per second, or something like that, hopefully they would spot that would be ludicrous. That would have gained amazing speed, and would probably be causing an enormous hole in the ground. So yeah, mechanics is really, I used to hate it as a child because I didn't care about the applications of math. I just enjoyed doing maths for the sake of it, and would just do the calculations and leave it and not think about what it actually meant. But for many students, this is the enjoyment. This is the time when math actually is useful. And throughout mechanics, there's a lot of opportunities for them to really think about what is actually happening.
Mm-hmm.
So we could have done this by splitting it in two and thinking about the upward motion and then the downward motion, but there's no need because that, you know, you can do that. And you'd just be doing a little Subat equation for the upwards bit, a little Subat bit for the downwards. But there's really no need because you've got the direction sorted, and provided you've done that and you've got all the signs right, that is absolutely fine. So that was all I was going to do about kinematics. And I've attached on Student Central, there's a lot of sheets with questions on it, so you can practice doing this, and it's got all of the answers with it. So I haven't particularly put anything on here right now, but in fact I can show you one. Here we go. constant acceleration equations. So you can just get them started as well for the kids, simply giving them the numbers. So as you can imagine, they always find it difficult when the maths is then wrapped up in real life. So
In text,
yeah, in text, exactly. So just getting them started with ones that you've just got absolutely massive like this, and just saying, okay, let's just get you writing down those equations, tick the ones, so write down your SUVAT, tick what you've got, tick what you want, and pick the right one, substitute it in. Just get them doing that to start with. There's loads of questions there, just doing that. That will just get them used to manipulating those formulae. Then they can start to do this. So a car accelerates from rest uniformly. So they write SUVAT, and I tend to get them to. Oh, no, I can't put it on there. No, if I do it on here. I know they do it this way like this, but I actually get mine to do it like this. So I write the SUVAT downwards like this, and get them to write it next to it, so that then they can see
so you
directly
can
what
put in the
they've got.
values.
Yeah, so they've got S is -1, U is 12, B is what they want, A is -9.8. So they can then see that they've got those, but then they can either take them, oopsie, or whatever, but generally they can then just see what they've got, and they can decide what equation they want. Saves them sort of doing it twice, and they've got all the values there as well. So this sort of thing, as I've just sped through it, is a good couple of lessons, spent just getting used to the equations, doing horizontal motion before you then introduce gravity. So you'd spend probably 3 lessons doing all of this. Going to move on to Newton's laws of motion, which is really the crux of mechanics, and you will definitely come across them, because we say a couple of them just generally in life as sort of generic things. So we're going to start with the first one. A body will remain in a state of constant velocity unless acted upon by an external force. It's enough to make the students just fall asleep, isn't it? But what it's saying is, if you've got an object and it is just speeding along, constant speed in a circulation, it will remain like that, and it will just keep going, keep going, and keep going, unless something happens to it, so some external force. Oh yeah, and it can be stationary. So state of constant velocity could be 0, so it could just be stationary, nothing's happening to it, or it's going at constant velocity. Now the external force, a force is just a push or a pull in a particular direction, and that could be anything. So you've just got something speeding along, constant speed, say it's a car, and it just remains in that constant velocity, and then you brake and apply a braking force, which means that it stops. Very well, it gradually stops. This doesn't seem like it's saying anything particularly amazing, does it? But I think Newton was just putting down things that he had noticed, and everyone was like, wow, who knew? So the study of things moving, mechanics basically, is all about forces, because the motion is all related to forces. So if it moves, how it moves is all about the forces acting on it. So Newton's laws of motion and the rest of this webinar are all about forces. So let's think about forces. trying to pull a body in different directions. Now, first of all, we need to model the body as a particle. So we draw it as a small dot. And what that means is that we don't have, it's all in the same plane, is what we mean. So that P needs to move. So now it's all in that flat plane that you can see. We don't have it dragging, so it's all happening from its centre of mass, which is right here. We don't have it pulling it, a bit of it over here and a bit of it over there. It's all at one point. So, as it says, in M1, they're only ever considering forces in one plane. There are not, it's not in, we don't consider forces in 3 dimensions at all. However, the direction definitely has an effect, because if one's going that way and one's going that way, ultimately, which way do you think this is going to go? If you've got 2 forces pulling on that, what's going to happen to that object?
Well, it's going to break in two.
Well, yeah.
It's going to have to go with the stronger force.
It goes, the forces combine together, actually, and we add them to get what we call the resultant force. So we often describe forces in terms of vectors. So I don't know if you remember when we did vectors and adding vectors, but it's exactly the same. You draw them nose to tail and then find the triangle, the line that goes between them. And I wasn't going to do that today. I was just going to sort of move on and talk generically about forces. Now, forces are measured in newtons. Yeah, we don't have to write them on here, but we use that when we as our units at the end of the calculation. And a newton is it's just a big N. It's a big N. So just going back to what we were talking about, I was talking about weightlessness. Now we use weight when we talk about our weight. We are actually talking about our mass. This often causes quite a lot of argument in the classroom with the children, because they're like, what? Well, why do we need to refer to it as weight? Why don't we just call it mass? I don't know. I do not know. Mass, basically, so when you say I weigh 60 kilos, actually, you are talking about your mass. So your mass is 60 kilos, not your weight. So this is where they're all going, oh, what? Everyone's been telling me this wrong all my life. Yeah, well, I'm sure I'm getting used to it. So weight has both magnitude and direction. So effectively, your weight is actually in newtons. So weight is one of the main forces that we generally will be considering. And that's the same. So yeah, talking about forces that you're going to meet, the weight of a body. So that's its mass under gravity. So the mass under gravity means it's made up of kilograms and acceleration. Tension is one of the forces that we'll meet. So that's what keeps a string taut. And then there's the contact force between 2 surfaces, which is generally made up of 2 things. The frictional bit, which goes along the surface against the direction of travel, and what we call the normal reaction, which is a force perpendicular to the original surface. Look at the time, which is 11 o'clock already. Sorry, need to give you a break. Must be parched. So I'm just thinking, let me just finish off what I'm saying here. So we sometimes, well, often talk about the contact force and talk about its different components. But I'm just going to show you these forces. So here's what we've been talking about. Weight, the force due to the gravitational pull. Friction, which occurs when 2 objects are in contact. So here we go. Here comes a mouse. to push this book, and he's pushing it, but there's friction from the table, so you can't push it. And you push it with your finger, the friction is, so you are pushing to the right, the friction is in the opposing motion, so that will be to the left. So you can only push that book if you overcome friction, so your force has to be greater than frictional force. So if you think about contact forces now, if you're sitting on a chair, I forgot to change the timing on this, so it's doing it all fast. So you are sat on a chair, there you go, then there is a person there, they're very grey, sorry. Their weight is acting downwards. Oh no, look, they've not appeared on the screen. Stop it. Sorry, I'm trying to do that. So this person is sitting here. They've got their feet. Can you see him? I don't know if you can see him.
Yeah, I can. Yeah. He's faint, but I can see him.
He's very pale. He's fading away. Well, that's the problem. It's a stick man. He's not eating that. His feet are pushing into the ground. That's part of his weight, and his self on the chair. So he's got a contact force from the ground, and he's got a contact force from the chair acting towards him. If we did not have these contact forces here, we would fall through chairs and through the ground. So this does seem like this is just I imagine at the time Newton was just like, wait, hang on. I figured out that there's a weight, there's a gravitational pull, and there's a force acting downwards caused by my mass and that gravitational pull together, which we'll call weight. However, why do I not just keep falling through the ground? Oh, hang on. So the ground must be providing some sort of force. What shall I call that force? So he called it the normal reaction. So in response to our weight, there is another weight pushing us upwards. And I think I've put it a bit later. But that leads me on to Newton's third law, which you will probably have come across, which is for every action, there is an equal and opposite reaction. So that's where that comes from. It's because for the force going down, there must be something coming up the other way in order for us to be supported. And the same if we lean back in the chair, there is then extra friction as well as the back of the chair. So air resistance, again, we don't really need to consider unless we're talking about parachutes dripping off the if we look at this crane, we've got tension from the parcel upwards, but also from the crane downwards. So those tension, again, equal and opposite forces is what keeps it, effectively that's when we say in tension, keeps it taut. Okay. And then compression, we won't be talking about that much today. That's the opposite. It's just tension in the opposite directions, basically, in order to prevent the trailer bumping into the car. So we've used different letters for these, as you'd expect. Weight we call W, tension T. Now friction is a bit tricky because we call the resultant force F, which means we call the friction FR. Okay, so we write it F with a tiny r there. Otherwise it can get very confusing. It gets unfortunately a little confusing anyway. But just need to make sure of that. And the normal reaction, you can use an N or an R. I tend to use an R because we measure things in newtons. Otherwise, we've got a few too many N's. That's just me going through that. And then often we just call other forces anything we like. We call it P because it could be a push or a pull. But you can choose whatever letter you want. And then this is just talking about the lines. So forces, we use just one big arrow. For velocity, we tend to use a little arrow without the triangle. So we use a triangle arrow for force, little velocity arrow, and a double one for acceleration. Anyway, do you want to have a break? and get a cup of tea?
Yeah, a coffee would be good.
Yeah. Okay, you go do that, and I'll go get a cup of tea, and I'll see you back here
I'll
in.
see if I... Yeah, I'm sorry. I thought it started at 9:30, so apologies for my lateness.
Oh, right. That's fine.
I've just picked up your email to
Oh,
say I'm
okay.
here. It's just us and just me. So
That's
okay.
fine. Yeah, yeah. No, that's
So
fine.
apologies.
I need to go at 12:15, unfortunately, to pick up
No worries.
the kids. But we'll have a if we have a quick break now, and then
Yeah, no worries. I'll just grab a coffee, come
yeah,
straight back,
and
and
yeah,
see you when you
cool. I'll
get
go
back.
grab tea.
All right.
Okay, see you in a sec. A minute, 5 minutes. Let me know when you're back. Are you back?
I'm here.
Oh, hi. Okay, great. So that was just me sort of doing a quick sweep through the names and arrows we use. Really, I'll just, you go back and look at that. Anytime you should require mechanics. But here we go back to Newton's first law again. So this is the saying that it stays at rest or continues with constant motion unless a resultant force acts on it. So I'm using the words resultant force now because that means we could have a variety of forces acting on it, and we add them all together to get this resultant force. So we have a parcel resting on a table, stays where it is. But if you're in a moving car and you brake suddenly, you would continue at the same speed, which is why you have to wear a seatbelt. Because if you were to brake suddenly, you would head forward, continuing at the same speed. So the seatbelt provides that resultant force. So obviously the guys that design the safety features inside cars have done a lot of mechanics, and they will be putting in all of that information to figure out how strong the tensile strength of the seatbelt needs to be in order to provide resultant forces up to quite, well, obviously probably 100 miles an hour, I imagine. So that the seatbelt itself will not break and can provide enough force to slow you down. However, just because there's no resultant force, so the resultant force, may be zero, but it doesn't mean there are no forces if it's zero. So look at this parcel lying on the table. I know I whipped through all those forces that you might come across, but what forces do you think are acting on that parcel lying on that table?
Well, I won't use names because I don't remember them. There's the force of the table keeping the parcel up, and there's force of the parcel keeping the parcel down.
Right, absolutely, well done. So there's the weight. Yeah, the weight of the parcel is one force. So it's the mass of the parcel due to gravity. And the contact force of the table. Yes, there's the weight of the parcel acting downwards. And so if the table wasn't there, it would just fall on the floor. And then the normal reaction, which I call R.
R, yeah.
Yeah, I tend to call it R to avoid it being confused with the units, newtons. So although there is no resultant force, because it's not going anywhere, because the resultant force is zero, I will say that. Oh, and we model it as a particle so that the forces are acting at one point. So the resulting force, this is called resolving upwards. So when we are finding the resultant force, we are resolving. That just means taking into consideration the forces. And we are thinking in an upward motion. So positive forces is R. R is a positive force. And because we're thinking upwards is positive, then weight is a negative force. So R minus W is zero. There's no movement happening here. There's no resultant force. They cancel each other out. And that's basically Newton's third law. Here's where I put it. When an object exerts a force on another, there is a reaction which is equal and opposite in direction to the acting force. So every action has an equal and opposite reaction, and thus they are equal. So, thinking about a few scenarios, you've got a pencil balanced on two rubbers. What forces do you think you've got?
So you've got the weight of the pencil
Yeah.
onto the rubbers. You've got the resistance of the rubbers onto the pencils. You've got the weight of the, I guess, the rubber and the pencil onto the table, and the resistance of the table onto the rubbers.
So that's true, actually. I don't think I've thought about the weight of the rubbers. Let's see. Well, the weight of the pencil, and
I'm going to say, if we include the pencil and the rubbers as one particle.
yes, I think this is the type of thing that actually they wouldn't give them in M1, because you can't model this as a particle, I don't think, because the weight, well, you can. You just have to combine these two reaction contact force, because they're not symmetrical. Now, we generally assume that weight happens from the center of something. Obviously, when that's a particle, that's fine. Here we've got our contact forces, but you're right, I haven't considered. So I've put, if we model it as a particle, we'd just have one contact force, so you wouldn't be able to find what they were individually, but it would be easier to do other things. So I haven't actually included any weight from the rubbers or anything. This is a fairly unusual one that they probably wouldn't be given. It might come up in M2 when you think about, if you were to put a weight on the end of the pencil, we talk about moments and how the pencil might turn. But in M1 we're only worried about what's happening in this direction.
So can you go back?
Yeah.
So you clearly have R1 and R2. So why? Can you just explain why don't you have W1, W2?
Yeah, you're right. So these are the forces of the pencil on the rubbers. I think I should have been more precise and forget about the ground. It's tricky because you're right. We should also have a weight one and a reaction one. There should be those ones, just as you said, as well. But this general, and we could call this weight 3. So yes, there's the weight of the pencil.
Right. So because the pencil is one particle, is that why we only have one W?
Yes, for that.
And
Yeah.
the rubbers are two particles, so hence that's why you have 2 points of resultant force.
Yeah. So
resistance.
we call it reaction. That's reaction.
Yeah, reaction force.
Yeah, or the contact force. Yes, I think I might leave that one out actually in future, because it's quite confusing, because it's not a scenario you would need to that they'd ask you questions about particularly. And equally, this one's quite a tricky one that you wouldn't probably have questions about. So forces acting on a pencil. I mean, this is the thing with mechanics, it just gets you to think a lot about things you don't normally think about. Forces acting on a pencil, if you hold it between the finger and thumb.
Well, the force is through the finger and thumb to hold the pencil.
Yeah.
I guess the force from the pencil out, and then is there another force, the one that's holding it up in the?
There's the weight of the
weight, yeah.
So there's the weight of the pencil, and there's the forces, the contact forces from your fingers holding it in, and actually they are held up by friction. So there's a friction between your fingers and the pencil.
Yeah.
But yeah, it's so resolving upwards again. We've got friction acting upwards, weight acting downwards, and then resolving horizontally. Those two contact forces equal each other, which is why the pencil doesn't wiggle between your fingers. However, if you applied more force from the thumb or whatever, then it would push it in a particular direction.
Yeah. Brilliant.
So yes, all of this is.
Yeah, I'm loving this, but it's just for me understanding the.
Yeah, and I'm going very quickly.
Terminology.
Yeah, I'm going very quickly through it. This is something that it's very new to the kids. Although some of them, they might have done some of it in physics before they get to you.
Yeah.
But it's making sense of real life. You know, suddenly they're like, wow, when I hold a pencil, there's all this stuff happening. Mine often get into a discussion about whether Newton's just made this all up as a way to explain it. But even if he has, and he's created a whole load of terminology around it, it has helped us to then, for example, decide how strong seatbelts need to be to keep you in a car.
Yeah.
So although Newton has created all of this words and stuff to go around what he observed, we are able to utilise it. This one gets a bit ridiculous. You'll get all the kids trying this, trying to balance a pencil with a rubber on the end.
Yeah.
So what have you got going on here?
Well, I guess you've got the weight of the eraser
Mhm.
onto the pencil,
Yeah,
and then that weight down through to the finger.
yeah.
You've got the resistance from the
Yeah,
reaction
reaction,
from the finger up through the pencil, but you must also have something going left and right to stop it going left and right.
I think, again, we would have to model this as something very small that wouldn't be affected by it. So yes, you've got the weight of the whole thing downwards, but also you've got this force from the um, rubber eraser and the contact force from the finger, which possibly would be made up of a tiny bit of friction as well. It's difficult to know, but you kind of have to have this normal contact force. You'd think that there should be a now what they often do, you see, you'd think there'd be a contact force here too.
Mm-hmm.
I've left off an arrow between the pencil. Then let me think about this. The weight of the pencil is all acting downwards, and that. No, there should be a contact force going up between these two as well.
Yeah.
However, what often happens is it's just generally combined. So this from the finger, it will be the same force of just the same thing together. I think I'm creating more confusion by showing you this. It's getting me thinking as well. This is what I hate about mechanics. I'm sort of left there going, oh no, I don't know. So, a pencil leaning against the wall. I should really get on with it. We'll just do this one.
So there's resistance at the point of the pencil.
Yes.
To stop it sliding out.
Exactly. So that'll be acting this way and towards it.
So is that R1 and then
That'll be friction. Yeah, actually.
Oh, sorry, F1 and F2 on the wall.
Yes, we call it friction.
Yeah, as opposed to resistance. So friction 1, friction 2.
Yeah. So there'll be a friction there, and there'll be a friction there, preventing it slipping there.
Yeah. There is weight.
Yeah.
Going through the pencil to the ground, but I presume there's also weight going through the pencil to the wall.
So
I don't know.
Basically, we model the weight as one weight that will just come down from the middle. I'll show you.
Okay.
If I press. There you go. There's the weight.
Yeah.
Just acts from the center of mass, which is generally in the center of the pencil. And then, yes, I think maybe you said one. You've got the friction. Oh, sorry. Yeah. So then you've got a normal reaction there.
Yeah.
And again, as you said, where it's leaning against the wall.
Mm-hmm.
And to prevent it slipping, you've got friction going in that way and friction that way. So, good. So then when we resolve upwards, we've got contact force and the friction, and upwards and the weight downwards, and friction that way. So let's go back to our parcel. In order to draw these, we draw them as little squares, and we then can show that the forces are all coming out of the same place, basically. So here's our particle with its weight and its reaction. Now if we attach a string to it, we have an additional force, which is the tension in that string. Yeah. So we now say the particle has a tendency to move, which means that the contact force, the reaction, will also have a frictional component to it, going this way, preventing you from pulling it until, in fact, I think I might put this against. So yeah, friction always acts against the tendency to move. Yeah, so we could add these together and replace it with a contact force just like that way, but we don't tend to. And we ignore air resistance. So, do you think the particle starts to move or stays at rest?
If the equation is equal to 0, then it stays at rest.
Yeah, and so in that situation, basically, what you're saying there is, if that tension is equal to the friction, it will stay at rest. So when that tension overcomes the friction, then it will move.
Yeah.
And that's what Newton's first law basically says. So when there's no resultant force, we call it equilibrium. So we just basically say it's in equilibrium. So if you were given, for example, the frictional force and told it was in equilibrium and asked what the tension is, you can just say, okay, well, it equals 0, so we can find the tension basically. So friction is trying to prevent motion. As we pull harder and increase the size of T, the friction gets larger to try to prevent the parcel moving. So here's a bit of a weird thing in that it kind of pulls against you. And you feel that, don't you? You know when you're pulling something, it's almost as if you're pulling it and pulling it and pulling it, and then something goes. And that's the point at which your force has overcome the friction. The friction increases until it can no longer increase. And that totally depends on the slipperiness of the surface. But there reaches a point where there is no more friction available, and then it will start to slide. Let's now think that we're playing ice hockey, and a puck is sliding across the ice with a constant speed. So again, it looks just like the parcel. Are the forces the same?
There's no tension.
Yeah.
There is friction, there is reaction, and there is weight.
Yes, exactly. As you said. So there was an original force that hit the puck. That's now gone, and the puck is just continuing at constant speed. But what do we know? Think about this. Can you see from the diagram? There's definitely a resultant. Yeah, because there's no force to balance the friction, the resultant here won't be 0, which means that if the resultant isn't 0, from Newton's first law, we know that although it's got a constant velocity initially, what will happen?
Well, I guess it's pushing against gravity. Is it gravity? I don't know. It's going to slow down
Exactly.
unless the velocity is constant.
Yeah. So this is what happens, isn't it? You send a puck across ice, it will continue at a constant speed because there is very little friction, but actually it's not really a constant speed. It's very gradually slowing due to that frictional force. So the frictional force slows it down. So if we assumed the frictional force was so small that we could ignore it, then effectively it could continue moving with constant velocity forever and ever and ever until it hits something, obviously. So here we now have a pencil being towed by a mouse. What forces have we got on this one?
Well, there's friction on the pencil and the mouse. There's weight from the pencil and the mouse, and there's reaction from the floor or wherever it is onto the pencil and the mouse. There's also the where are we? The weight, let's say, the horizontal weight of the pulling the pencil backwards, and the I guess the mouse propelling. So the spring.
Yeah. So
yeah.
Actually, both of those we model as tension in the spring.
Yeah. Ah, so that's tension. That's
yeah.
it.
So
Is that T1 and T2?
Yeah.
Or just
Exactly.
T?
Yeah. So there we've got our. Well, in fact, sorry, I should have read this again. On the pencil, you're right. So what we tend to do is actually, you're right. There is also the weight of the mouse, and this the mouse, and equally
Yeah,
he's got that
ignore the
one,
mouse. Yeah.
and he's got his sort of driving force and friction facing him that way. So we model his kind of driving force forms the same tension there. So you could call them T1 and T2, but ultimately they will both equal the same. So they just mean T. So yeah, that's tension. So if we now look at something going, oh, sorry. Yes, so the resulting force is 0 because it's going at constant speed, or if it's stationary, then it's 0. If he was getting faster, then we'll have an actual resulting force, which will hopefully be positive because it'll be him pulling it. So whenever, and this is the key thing that you've got to get them to do, because you know what the kids are like, they hate to draw things. They've got to draw diagrams, and the common errors are that they do tiny little diagrams, try to put all these different arrows on them, and it just is a complete mess. You can't see. They often miss out forces, so they forget about the contact force in particular. Or they break down the force into too many bits, and you've got too many bits to it. Another common error, friction being put in the wrong direction. Mass being shown instead of weight. So the mass weight issue, unfortunately, continues all the way through. They get confused. You'll see later why they get confused even more. I'll say later, but not much. So now if we're going to think about things happening vertically and the forces, we've got a light, inextensible string. So that tells me that the string itself has no weight and is not stretchy. Okay, so that just happens to be a string, basically. Got a particle on the end of it. What forces are there going to be on this?
So tension.
Yeah.
And weight.
That's it. Yeah, exactly. So effectively, you've got the weight of the particle acting downwards, and its reaction force in this case is the tension that is created in the string. So in this case, okay, yes, and as you can see, this is why we do the little triangles, and we've got to try and make them as clear as possible. That's just saying don't put them too close to the particle so they can see them. Oh, so don't put it too far up the string because we don't want the tension on the peg. We're looking at the particle. And that's often the case. Often there are additional forces, but we don't care about them because we are looking at the particle in this case. We're not worried about the peg and the peg's weight and the tension on the peg. There's no contact force because it's not in contact with the surface, so the tension offsets the weight instead. Now we've got forces acting on a body which is sliding down a rough slope with constant velocity. So what forces have we got going on here?
So there's friction, there is weight. There's got to be reaction from the floor that it's on.
Yeah, exactly. So yeah, we draw the weight always vertically downwards, even though there's a 30-degree angle on the slope. No strain, so no tension. And the other force is the contact force. So we say that the contact force is perpendicular to the slope normally. However, you can draw it, so the total contact force balances the weight. So you could draw it like that. I never do that though, because it's generally made up of two components. There's the reaction to that acts perpendicular to the slope, and then there's the one that acts parallel to the slope. Now the one acting parallel to the slope is in fact here made up of friction. So as it says, whilst this diagram's correct, we generally split it into the components. So we've got the normal reaction, which acts perpendicular to the ground, or in this case the slope. And then we've got friction that always opposes motion. So since this is sliding down a slope, friction is going to act upwards. So we know that these two are actually going to equal the total weight because there is no resultant force, it's constant velocity. So both of these are correct, but we don't tend to do this one because it's more useful to have both of them shown. And if it was at rest, then this one would be fine. It doesn't matter, there's no difference. But if it was moving, then in fact, as it was accelerating, this one would actually be wrong because there's a resultant force now. It's not just that one equaling that one. There's actually an additional force now. So we've got the friction, but if it's accelerating, there must also be, there must also be some sort of force, resultant force basically, that will be happening downwards. So let's now think about, finally, got a ring tied to two strings that's hanging down. What forces are you going to have? If you look at this first one here.
Right, hang on, so I'll say T1 and T2.
Yeah.
And weight.
Exactly. And that's the same on both diagrams. But here, because it's the same angle, in actual fact, it will be exactly the same tension. So you could just call them both T, because T1 and T2 will be equal. Whereas in this case, they won't be due to the different angles. And I haven't got into this at all, but anything where there's these angles, we end up having to resolve things still vertically and horizontally. But in order to resolve that horizontally and vertically, we end up using trigonometry. So we end up with like T1 cos 35 and T1 sine 35 as our two components. And I'm not going to get into that today because we don't have enough time. What I am going to look at now is, I think we've done masses of these, so I'll leave these ones. These are all just putting on the forces, basically, of these. And you've taught me through all of these as we've got along, so you're getting the hang of that. So I'll click through all this quickly, and it's there on the PowerPoint for you to have a look. But what I wanted to get onto was actually Newton's second law. So far, all of those we've been looking at have just been in They've been stationary or constant velocity, so they've been in equilibrium. There's been no resultant force, or the resultant force is 0. The Newton's second law is when there is a resultant force. So this is just actually showing how he got it. It's all to do with momentum. So momentum is mass times velocity. So you know when we were talking about the 2 Coke cans rolling down the slope, because momentum is a combination of mass and velocity, the reason that the bigger one gets down there is because it has a greater mass. So I'm just going to whip through this because you don't really need to know, but basically the force that occurs is the change of momentum over time. We then put in the Suvat equation and we end up with this equation, F equals ma. Have you come across that at all before?
No.
Okay, that is force is mass times acceleration. So the Newton's second law is basically this equation. It says that the resultant force, F, is, you get the resultant force by doing mass times acceleration. Here we go. So from Newton's second law, we get this equation. And it's measured in newtons, because it's kilograms for mass, meters per second for acceleration, and force is newtons. So that's just going to mean that when we are resolving, so I've put a load on here of questions. This comes from the sheets that I have also again uploaded. I'm going to see if I can get a pen and just show you the first one. So I've got a particle of 5 kilograms. So I'm going to draw my particle as a little square. Actually, no, on this case, I'm going to just its mass is 5 kilograms. Okay. Oops. So the weight acting downwards is 5 kilograms, and then due to gravity, I do a g because the weight is the mass and the acceleration basically. So the weight is 5g. The kids get that really confused because it is basically looks like grams, but it is actually weight. Now in this case it doesn't matter because this is horizontal motion. This particle is going this way, F, that's the force. Particle mass moving with acceleration. It doesn't tell me at all actually whether I've got any sort of friction or anything. But my acceleration, I use this double arrow, and that's 3. Now, in actual fact, I don't really need to know much more because I'm going to just use F equals ma. That's just mass, which is the 5. This is where they get confused again because they've been thinking about weight, and then they're required to use mass times the acceleration. So the force acting on, I've reached the end of my board, I can't see to write an M there. That is an N, sorry. So the force that is causing this particle to move is 15 newtons. So all of these, sorry, go on.
No, just said my battery is dying, so I'm moving to a plug. So you can keep talking. I'm just.
No, that's fine. So here, let's just look at number 4. A particle of mass 10 kilograms is pulled along a smooth horizontal plane by a horizontal spring. Oh gosh, that's a really smooth horizontal plane, isn't it? Okay, let's imagine it is. Oh dear, there's the weight, and I've got tension in the string, so that's my tension. Now it's smooth. So that is telling me that friction is 0, so I do not have a frictional force acting the other way. So I've got my weight and reaction. Now, actually, for these diagrams, there's my reaction on that one. Oops, that should be out of the middle. The weight and the reaction, it doesn't matter because it's not having any vertical motion. What's important is that I've got it moving along at 5. And again, so F is my T. So T, again, equals MA, which is 10 times 5. So that one's moving with 50 newtons. Again, I've reached the end of my screen. Like that. So this is all of these ones is just a case of rearranging F equals MA. So I'm going to leave that for you to do when you've been through this. And the answers have also I've uploaded them to Student Central. Now, when we know the motion's in a straight line, we just consider it all in the same direction. So we don't use vector notation. The reason I'm saying that is because they used to underline the F equals MA. The F and the A are vectors, we underline them, but you don't need to. Equally, this little line here is due to me changing it and not moving it. That's normally under the G, because again, G, being acceleration, it's a vector. So you can put a little underline under it, which is quite useful actually for them not getting it muddled with ground. So let's now think about a particle in a vacuum and you're dropping it downwards. So you've got the weight, you've got the acceleration, which is due to gravity, G. So that means that by Newton's second law, weight must equal mass times acceleration. So the resultant force W is just mg. So generally your weight is mg. So you could calculate your weight. So yes, if you know that you are 60 kilos, then you times that by 9.8 and you would know your true weight. So you get all the kids to calculate their true weight according to what Newton called weight. So although magnitude of gravity varies slightly over the Earth's surface, we take it as an average of 9.8. I think it depends on, sort of whether you're up a mountain and stuff like that, but I don't really know enough about gravity. So let's drop a pebble off a cliff, straight down. We have to assume it falls in a straight line, and there's a resistance of 0.06 meters. So then instead of resistance, that would probably be a tiny bit of air resistance, and not much else really. So again, we draw a diagram showing the force downwards. So the force downwards, as we've just talked about, is mg, and that's what I was drawing on my little diagrams before. I was writing the weight as the mass and the acceleration due to gravity. So the weight is equal to 0.2 g. Does that make sense?
Yeah.
So we also know that there is a resistance of 0.06. And so what we want to find is the acceleration. So using Newton's second law, F equals ma. If we resolve downwards, oh yes, so this is what they're saying beware about. On the left-hand side of the equation is a force, which involves weight, but this mass, this m, is the mass. And you get the students putting the weight on this side and the weight on that side, they cancel out, and they get acceleration of 0. They get very confused. So I wouldn't mention it actually. I think I'd just wait until anyone fell into the trap and then say something about it. So we always resolve in the direction of acceleration. So we're going to resolve downwards. It just makes things easier. So downward forces first. We've got 0.2 g, the weight, and a negative force is the 0.06 because that's actually acting upwards. Equals mass, which is 0.2, and what we're trying to find is acceleration. So although it looks to them like they've got a letter here they need to find, they do know the value of that. They know that that's 9.8. So they can replace that and work it out. So the acceleration of this particle as it's dropped off a cliff is going to be 9.5 meters per second. So they can combine these questions with then saying, okay, so what speed was it when it started? So they can then combine that with the Subat equation. Now we've got some acceleration and how long they can tell you hopefully more stuff. So that was assuming that air resistance is constant. So that's another assumption that we definitely had to take, because otherwise it would be too complicated. It's not actually constant because it's proportional to velocity at low speeds, and then sort of velocity squared at higher speeds. So when we were talking before about dropping things out of aeroplanes, it's going really quickly initially. So the greater the velocity, it's going to be going greater air resistance, and then as the velocity slows down, it's still proportional to the velocity. But we just assume that there's no air resistance, always constant. So I think this would probably be our final example. We've got a child of 50 kilograms. Really? It's quite a large child. Standing on the floor of a lift. Okay, we've got a teenager.
He's American.
Oh gosh. On the floor of a lift whilst it's moving up. So the lift is moving up. Find the reaction between the child and the lift. They love lift questions. They're their favourite ones. So here we have the lift is drawn like a pocket, and you've got a child drawn as the square. So what forces have we got happening on? So we're thinking about, so what's the reaction between the child and the lift when it's accelerating and decelerating? So what are you going to draw on this?
So I'm going to draw a weight arrow down from the child.
Yeah.
I'm going to draw a reaction arrow up from the lift.
Yeah. And what's your weight going to be? What, because you can write the value of that.
So that's 50 MA, isn't it?
So 50 is the M, yeah, and the A is G.
Is
the G,
which is 9.8.
Yeah. So we tend to just on the diagrams write 50G, and then when you come to calculate it, you replace the G. And were the lift not moving, then the reaction would obviously just be 50G, so it would just be the same as the weight. However, because it is now accelerating, so getting faster or decelerating, depending on which bit of the question we're doing, you have to take into account that the reaction will actually change in order to accommodate that acceleration. So yes, here are our forces, as we said. So we also need to draw the acceleration arrow on. So for acceleration, it says the lift is moving up, so we draw the acceleration on, and it will be 2 little arrows, and it's going at 2 meters per second squared. So we resolve in the direction of acceleration. So we draw a little sort of bracket with an arrow in, like this. I know they're writing the resultant force equals mass times acceleration. Generally, just always write F equals ma. So the student should always write F equals ma to hopefully get them some sort of mark. Then they show their arrow, and they go upwards will just be R, downwards is 50G. So you end up with R minus 50G is the mass, which is 50, times the acceleration, which is 100. Rearranging, you end up that the reaction is 590 newtons. Now, what changes if it's now decelerating?
The meters per second it turns negative, does it?
Good. Yeah. The diagram looks exactly the same because the lift is still moving upwards. It's just slowing down, but that becomes -2. Excellent. Yeah. And then you just sub it in the same. F equals ma. So r minus 50g is just 50 times minus 2, which just means that the reaction force is smaller and is only 390 newtons. Good.
So the arrows for acceleration, they're still pointing the same way,
Yes.
even though it's traveling in a different direction.
So it's not traveling in a different direction. The lift is still moving up.
Oh, sorry.
Yeah. No. Do you know this?
Decelerating.
Yeah. No, it's very, very. This is the problem with vectors. Well, it's not. This is why it's. But you know, if you for example, if you were accelerating in a negative direction, so if they were going downwards, but you had defined upwards as positive, and they were accelerating, then that would be negative. But if they were decelerating downwards, that would then be positive. And the students find this very confusing. So negative can be that you are going in the opposite direction, or that you are slowing rather than speeding up.
Yeah.
So yes, that is why it's negative. The lift is still moving upwards, so the acceleration is happening upwards, but it's a negative acceleration. It does say, how could we find the normal reaction if the rope supporting the lift broke? So they're plummeting to their death. The child's plummeting to their death now.
Okay, so is the acceleration 9.8 as opposed to 2 then?
Yeah, we could think
No,
so, wouldn't you?
yes.
I don't know. And I'm just thinking, and the normal reaction, would there be a normal reaction? Is the child, because if you think about a lift dropping, you lift up, don't you? As it
Yeah.
plummets. You lift up, and that's all because of all of this. Because the acceleration has got so much. Yes, you're right. Because the acceleration, if it's gravity, g, then your weight is not sufficient to keep you down on and provide a contact force. Yes, the lift drops with acceleration due to gravity. Yeah, there it goes. And thus, when you put it into here, going downwards, 50g minus r is your mass, 50 times 9.8, which actually is just 50g again, which means that there is no resultant force.
Yeah.
There's no contact force happening there, because as it plummets, you basically, or your weight is the same as that acceleration downwards. So if a lift plummets, yes. So I was always told if you are in a lift that plummets, you should jump, because there's no contact force. You are trying to avoid the force as it forms contact. So as that lift then hits the surface that's down here, hits the ground, it's going into it with this huge force of 9.8. It's accelerating at 9.8, so it'll have got faster and faster and faster. Hits the ground. With your combined weight in it, there's going to be this enormous reaction force as it hits the ground, which you don't want to be part of, basically. And in fact, it would probably cause the whole of the bottom of the lift to crumple, and kill you. Anyway, so yes, you'd feel weightless, but I think you basically do not want to be anywhere near that lift at the bottom of it as it hits the bottom, because that force is going to be so great that you can't take that. So yeah. Anyway. So yeah, absolutely, ouch. Let me just go. So, for example, a package of mass 8 kilograms is lowered by a vertical cable. There we go. With a downward acceleration. So again, we've got our weight, which is 8G. We've got our tension here in the cable, and it's got downward acceleration of 2. So this is why these are all really important, because then you can see from the diagrams which direction things are going in and what's going on. I know that this is a very simple thing for the kids once they get it. They just go, well, it's F equals MA. I just bung it in. That's all very well, but they want to see you say that you're resolving downwards. So yes, you write F equals MA, and then downwards we've got 8G minus T is mass, that was our 8, times our acceleration 2. And then you can see that T is actually going to be 8G, whatever that is, minus 16. And they can calculate that. So this has all been really just a lot of thinking about what is going on in very basic situations that we take for granted every day, and applying Newton's 3 laws, which are that without any external forces, a body will continue at rest or in constant velocity. If there is a force, a resultant force, then its mass is proportional to acceleration, and therefore we can calculate the resultant force using F equals ma. And his third law is that for every action there is an equal and opposite reaction, which is why the downward forces equal the upward forces. And those 3 laws basically govern the whole of well, motion and how things work. So hopefully, if you ever end up teaching it, you will find that you can inspire quite a lot, particularly the boys, I suppose, with this. And try not to put too many of the girls off. As I used to find, I really didn't enjoy this. Because of the whole, oh, have I lost a force? What have I got? I've got so many forces. And always remembering, no, wait, I'm concentrating on the particle. I want to know about the forces just in the particle and breaking things down into it. And the final thing I was going to show you, but I don't know if it will come across. In fact, let me load up this guy. Oh, let me unplug this. You won't be able to hear me, but hopefully you'll be able to hear him. Can you hear that?
Yeah.
There you go. It's things to do with your class.
Very good.
I know. It's a bit of fun and quite good to show the kids. They'll have it going round and round in their heads. Oh no, I've just got they're going again. Ah! Look at
That's all right. I just thought it was going round and round in my head.
that. Hang on. How do I get this to stop? Stop. Stop. There you go. Right. So I've put the link to that. That's Mr. Chadwick, who is, I think, a maths and physics teacher somewhere. And that must be a further maths class to be able to, well, to only have one girl in it and to also get them all to join in. Pretty amazing. But yeah, and that actually also includes a bit about friction and how we calculate friction, which is mu, or the coefficient of friction. But I'm not going to get into that today. In fact, that is the end of our incredibly quick foray into Newton's laws of motion. But if you have a go through all the sheets on the Student Central, then hopefully it might start to make more sense where you can sort of go through this PowerPoint slower. I've also uploaded it onto there as well. Yeah, otherwise, any questions?
Hang on. No, I'm going to have a good look through that now. I've got about 45 minutes, so I'll see how much I can crack out. Are you in Warwick?
No, because I thought it was the following week and didn't realise that, because is it the 10th and the 11th?
Yeah, Thursday the 10th, Friday the 11th.
Yeah, my daughter's got an inset day on the 11th, and I had already booked near here. They have an ice rink at Winchester Cathedral, and I'd already booked us to go ice skating, unfortunately, that day. So I did sort of think, oh, can I make it up to Warwick Thursday night? But I don't really know what you guys are going to be doing.
Drinking?
Well, exactly. I know, and driving all the way up to then get back for ice skating at 9:30 on Friday morning. I just thought, I don't think it's going to happen, is it? It's a bit of a shame. So it's a shame that it wasn't just the day before, really. So I don't think I will see you guys again. Unless, are you going to go to your graduations whenever they occur in Brighton, maybe next summer? I don't know.
Yeah, definitely, yeah. So I believe it's in February.
Oh, is it in February, is it? Oh, you've disappeared.
That's the loose information we've been given.
Okay.
I'm back. Yeah, I've just kept in and off because my cleaner's doing the hoovering. So
oh, right, okay.
Limits background noise. I don't know how much of it's coming through on the microphone.
Only a little bit.
Okay. So graduation is on.
Okay. So
as it were going.
Yeah. And is that down in Brighton?
Yeah, that's what. Again, they've not released anything, but they said, look, they expect it to be in February and they expect it to be in Brighton. So we haven't got anything more substantial than that to go.
Right.
That's on the assumption graduate.
No.
Yeah.
Well, did you have your results through from everything? Have you had your results through?
Yeah, we did. So no, we've submitted one on Monday.
Oh, right. Okay.
We've got another one to go in in November, but that's pass or fail. And then there's the two based on your, I guess, teacher standards and the school's assessment.
Yeah. Yeah.
So yeah, it's those final bits. And the last one I handed in, I think I did terrible.
Oh.
But, so
Well,
I'll
hopefully
balance
all
that
balance
out.
out.
Yeah, I don't know. I'm in a good place anyway. School's fantastic. Teaching's going well.
Cool. Are you staying at your school going forwards then?
Yeah. So did you go up on the recent Cohort 3
Yeah, I was at Huddersfield last
gathering?
week. Yeah. So I've got
Any
another 4.
mathematicians?
Yeah, I've got 4. So I've got 3
Another?
men and a woman this time.
Ah,
Yeah.
brilliant.
Yeah. So
Excellent.
yeah.
So we're gathering momentum.
Yeah, hopefully. Oh, that's quite good about
Hey,
so yeah, so if I don't see you again, good luck. And you can always email me anyway if you've got any, questions whenever. And
yeah.
yeah, I'm sure you guys will all pass
And
on.
you'll ignore us because you're not getting any money now.
Oh no, it's all fine. Emails are no hassle to respond to them.
Well, if we don't bump into each other again, then I appreciate so much your time, your patience, and your ability to get things across to somebody as quick thinking as me.
Oh, that's all right. Well, it's been a pleasure.
So it's been really appreciated. You've helped me make my dreams come true to become a teacher. So I'm really pleased. I'll be hating you in 5 years' time, but at this very moment, I'm very appreciative of everything you've contributed.
Have you got any A-level classes this year?
No, I haven't. I'm going to sit in on a year 12, only once a fortnight, and a year 13 once a fortnight,
Right.
because that's all my frees allowed. But I'm
Yeah.
hoping after Christmas I can get a little bit more in as we go 5 days a week then.
Yes, of course.
But yeah, they want me to teach A level at some point, but it's not in my contract.
Right.
But I want to do the A level as well.
Yeah. Oh, right.
So
Actually, physically do it yourself.
yeah, because I haven't got it, and I think it would be really nice to get that achieved. Now that the cleaner is almost on top of me.
Yeah, that's all right. Right. I will stop the recording